Hey everybody, welcome back. Today we're going to talk about model selection and how to try to find all the hyperparameters and algorithms and features that you might want to use for the best possible classifier performance. Now, before we get into the technical details, there's a couple of points for logistics on the class that we need to take care of. So most importantly, from my standpoint, is that it's really time for all y'all to try to work on the final project. And if you haven't already, now is definitely the time to do so. So I've released on Canvas a fairly full description of the project. So I'd like you to take a look at that and start to work on it if you haven't already. Now, back when I wrote the syllabus, I said that you would be fine to do group projects. I'm kind of changing my mind in that I think the default should be a single person project. And one of the reasons I think that is that today's lecture will give you a lot of the tools you need to really get most of it done. So I think it's very doable in the single person level. Now, in terms of a group project, if you were counting on doing a group project, it was something you were looking forward to or you had ideas, then I'm going to allow group projects, but you have to convince me that this group project is a good idea. So I'm going to limit it to 3 people, and you have to come with a proposal. You have to come to me in email or in person, I should say in Zoom, or talk to a TA if you're closer with them. Do that and lay out what you think you're going to do, because a 3-person group should definitely be able to do around 3 times the amount of work that a 1-person group is going to be able to accomplish. So please think through what it is that you're going to do to extend the project. All right. So yeah, please, if you have questions, come talk to me or the TAs. Write stuff on Piazza, bounce ideas around. Let's see what we can do. I do know that there are a couple of people that are already working above and beyond the project itself, and I'm okay with that, right? I mean, if this is your groove and you want to do something a little bit fancier, that's super awesome. All right? But just do check in with us. Don't start off on your own. If you're going to do something a little bit different than the project proposal, you do need to at least run it by us. All right. Now, things that you probably are kind of happy or sad to hear about is the exam has been returned. You now have your 3-day period of asking for regrades if you find something that's wrong. Overall, this exam had a little bit more variability, I think, than the last one, interestingly. I feel like, from what I've seen so far, that the vast majority of you had a pretty good grasp of it, and there were certainly people who aced everything and the extra credit. So is an interesting spread this time. Also, I'm a little concerned. If you thought that the test was still too long, would you please let me know? I'm concerned because there was not any real huge reduction in the amount of time it took people to do this exam. And I don't know if that was just people being super thorough, so they were using the maximum amount of time possible to get the maximum points, or if it really was almost as long an exam as the last one, and even when I think I'm cutting them down, I'm not doing enough. So please, I would love some feedback. Piazza, email, whatever. Okay? And lastly, on our logistics, I just want to remind you that coming up in just a little bit more than a week is our guest lecture, and it will be Eugene Izhikevich, who's the CEO of Brain Corp, a company that's spun out of Qualcomm, which makes robotic machine learning systems. These robots do things autonomously to, for instance, clean industrial settings or move parts from one place in a factory to another. And it's a pretty cool situation. Eugene both is a mathematician who's done some pretty impressive brain modeling, and he is also somebody who has hired his fair share of machine learning people. So definitely worth your while to come hear a perspective from somebody who's both invented algorithms and hired people who invent algorithms. All right, well, let's get on with it. So selecting the form of a model, right? Tuning a model, getting it into shape. I just wanted to make sure that we're all on the same page, because we're going to talk immediately about hyperparameters. So when people say parameters of a model, they're often talking about that weight vector, W, which is something that is learned by the model. In contrast, when we talk about a hyperparameter, well, we're using the word to mean something that you, the experimenter, is setting. Okay? So the hyperparameter is maybe something like the number of nearest neighbors you're going to use. Okay? The K, that's a hyperparameter. If you're doing a support vector machine, then the hyperparameter might be something like the regularization parameter, C. And along with that, if you're going to use a kernel SVM, which kernel you're using. Okay? So these things are hyperparameters. They are not set during the learning process. They are set either by the human or by some automated process that's not the algorithm, right? And by automated process, I'm talking about model selection. I'm talking about whatever we're going to do to try to make sure we've got the best possible version of our model for solving our task. All right. So what is a model selection process? Ideally, in the world of we have all the data we could possibly ask for, the model selection process is dead dog easy. Okay? All we need to do is we need to split up our giant amount of data into 3 separate sections. One for training an algorithm, one for validating the algorithm, and that's the part that gets used for model selection, okay? And then finally, a test set. And the test set is only ever used once we have our final version of the model. So it looks a little something like this, okay? So we have an enormous amount of data, and we split it into training, validation, and test sets. So what happens is we take that training data, and we're going to try a bunch of different things. Each one of these little hyperparameter value circles is a different version of our algorithm, a different version of our model, with the settings in a different place. So we're going to do all this in parallel. We're going to take the same inputs in the training data and run them through 3, 4, 3,000, 4,000, whatever, different versions of this model. Okay? And coming out of that, we get all these different model versions. Now, which one of these 3,000 or 4,000 models is the one we want to use? Well, we have to evaluate it on the validation set. So we take those models, we run them through that validation data, and we get predictions coming out, and we check it against the true actual values. And that leads us to a performance estimate. Okay? So our model predicts with the data the new values. We have true values, and we compare them against each other. Whichever one did the best, had the fewest errors, or whatever metric we're using, that is our best model. All right? Now we've got our best foot forward. We know which one of these thousands of models is the one that goes best on our validation set. Finally, we need to go ahead and try an idea of how good is this model in the future, right? We need to see, is it going to generalize? Are we going to be able to get more data from the same underlying process and find out how well we think we're going to do with that new data? So this is where the final test set comes in. The test set, we run the best model. So actually I should say this. We take the best version of the parameters, not the best model. We take the best version of the parameters and we retrain it on all of the data that we have worked with so far, both training data and validation data. Not the test data. Everything we've worked with so far is what we use. We retrain the best parameters into a new model which is fit on all of our training and validation data. All right, that model gets evaluated. We run it through the test data. We get the predictions and we have the true labels, and that gives us an estimate of performance. That estimate of performance is our assumption, our best guess about how good this algorithm is going to do with brand new data. Now, why do we divide things up into 3 separate chunks? Well, what we don't want is we don't want any leakage. We don't want, that sounds really gross, right? We don't want any leakage of information from the training data into our evaluation of how good this algorithm will do. Let me give you a personal example. I was working on an algorithm to do some prediction about 4 years ago, and there was a brief moment of insanity on my part. And I thought, oh my goodness, this crazy thing I've done. I've got this algorithm which is learning which are the best variables that it should use to predict with, and I can't believe how good this is. It was, beyond state of the art by a good long way. Well, here's what happened. I was accidentally using a chunk, not all of, but a chunk of my test data. And in so doing, I had gone from, yeah, nobody cares kinds of results to, oh my gosh, the best ever, merely because I reused a chunk of my test data into my training set. Okay? And that training set was doing, feature selection, right? It was trying to find the right subsets of variables that would best help the algorithm predict. So, moral of the story is, even a small amount of information leaking from the test set will make your belief in how good you are much better than it truly is. All right, so we hard separate, throw data into one of those 3 categories and don't reuse across. Now, the problem with that approach is that it really relies on you having an enormous amount of data, because if you don't have enough training data, then you're going to get a bad fit. So you're never going to get your algorithm as good as it could be if you don't have enough training data. Now, if you don't have enough validation data, then you're going to get a bad selection of whatever you're looking for, hyperparameters, features, models, okay? That you're just not going to be able to really know if you have selected, because there's always the chance with small samples that you get weird random stuff happening. And obviously, if you don't have enough test data, then you get a poor estimate of the generalization performance, okay? Usually we do not have enough data to completely have these huge separate training, validation, and test sets. So, and we know we need to not leak information from the test set into the validation set or the training set, because if we do that, yeah. All right, so what's a person to do? Well, the standard answer, and one which is often good enough, is k-folds cross-validation. So we've already talked about k-folds a little bit, but just to make sure you're cool on it, what we do is we take training data and we chop it up into however many folds, k of them. And every time we train on everything except one fold, and we validate on that fold, and we get a performance metric. Now, critically, we're going to do this k times, so this is 5-fold, right? We do every one of these 1/5 of the data as its turn as a validation set. We get 5 different performance levels, and we take our true performance, validation performance, as the average of those 5 folds. Other than that, it's the same process, okay? We can run this a bunch of times in parallel with many different hyperparameter values, looking for the best hyperparameter set for solving our problem. Now, once again, you still have to have a separate test set if you want to get a good idea of generalization performance. Okay? K-fold cross-validation has some things. So as we dial k back and forth, why would we pick a small k or a big K? Right? So let's consider 2 special cases. So those 2 special cases, k equal to 2 or k equal to the number of samples that we have, are the train test split, and this is called leave one out cross-validation. Leave one out, LOOCV. All right, so what happens when we split in half? We know we've lost half of our data, so we don't have enough power, maybe enough sample to get a really good fit, and we may not have enough sample to get a really good test. But if our data set's big enough, a train test split is good enough. The good thing about it is that because you've got half your data in each one of those sections, overall the statistics, the distributions of what's in each half are probably very similar, okay? But when you chop up the data into lots of little pieces, into a high number of folds, then your variability gets high, because in small sample sizes, and lots of chopping up means each sample is small. Well, in small sample sizes, it's easy to get weird stuff happening with random events. Maybe you completely lose all of one of the classes in one of these folds, okay? Stuff happens with randomness. So you get the idea that there can be a lot more variability as you increase the k. Now, because the variability is going up, we know the bias variance trade-off. So leave one out cross-validation, k equal to n, is the most unbiased cross-validation, okay? But because of that, it has high variability. When you have a single sample as your validation set at each point, essentially you either get a 1 or a 0 performance, right? You're either perfect at classification or you're crap at it, okay? So each slice is highly variable, but overall, the mean of leave one out cross-validation is pretty good, right? We're going to, on average, if we have enough samples, our average on leave one out cross-validation is going to be a pretty good estimate of performance, okay? Think about it as like when you're trying to estimate the probability of a coin flip, right? A coin flip is a 1 or a 0. If you only have 2 or 3 coin flips, you're going to do a terrible job estimating the probability of the coin and whether it's fair. But if you have 200 coin flips, you can be very certain that you know whether that coin is fair or foul. All right? So leave one out cross-validation is just like that. If you have enough samples, you know it's an unbiased and pretty good estimate, and that variability that I was talking about from fold to fold is going to even out. However, leave one out cross-validation is computationally very expensive. If you have 200 samples, you're going to be training the network 200 times. And that's before you're doing any kind of model selection, right? That's just for one hyperparameter value. You're training the network 200 times for a 200 sample. Leave one out. So things get hairy quickly. I have personally run things that took more than a month to compute when doing stuff like this. All right, so often we don't go to leave one out cross-validation. We stay with a smaller k. We know that small k's are relatively biased because they're not variable. How are they biased? Well, a small k is biased to systematically underestimate performance. It's biased. It's going to give you an answer of generalization performance that's worse than the truth. Why is that? Well, you're not, by having, say just 2 folds, you're throwing away half your data. You have less than, you have only the half that you've got left to do the training, so you know you're going to have less ability to fit well. If you gave your algorithm all of the training data, it would assumedly do a better job fitting the process. So that is how we systematically underestimate. All right. So now we can do even better. There are various schemes where we can do even better than k-folds cross-validation. Things that I'm not going to talk about that fall into this are various kinds of bootstrap resampling. Okay, we're going to cover that when we start talking about random forest classifiers. But trust me that there are many ways beyond k-folds cross-validation to get at model selection, feature selection, that kind of thing. So as I said, k-folds is often a good enough thing, right? It's simple. It gets you a pretty good answer. So most people will stop there. However, in those cases where you really want to squeeze the last ounce out of the data, you only have a few hundred things and you want to get the best state-of-the-art performance, it's been shown that nested cross-validation is about as best as you can do. Okay? So what is it? There's an outer and an inner cross-validation. Okay? So the outer cross-validation, we have our 5 folds. Okay? And we're going to take this chunk of the data, everything but this stuff, and we're going to train on that. But now inside that fold, we do another cross-validation, an inner loop of cross-validation. And what happens is we're using the outer loops. These are used to estimate performance. And the inner loops are used to tune the parameters. So how does this work? We do this inside with, if we have, say, 10 different versions of the hyperparameters, we do that 10 times with each hyperparameter set. Okay? We take all 10 of those and we evaluate them on here. And that gets us 10 validation error rates. And we do that again, but now we cross-validate on this stuff, right? And that's our test. Oh, sorry, not test, validation. And again. Okay, now we have 3 sets of 10 validation errors. We take the mean over those 3, and that gives us our estimate of performance for each one of the 10 hyperparameter settings. Okay, what have we done? We've essentially done cross-validation a few extra times, and we're going to average across it. And each time we've done it, we've taken a slightly different resampling of the data for doing so. Okay, this is called nested cross-validation. And it is a nice tool when you're trying to squeeze the last ounce. It is not the only tool, okay, again, but it's the one that I'm going to cover right here. All right, so when you are trying to do hyperparameter estimation, trying to select, sorry, not estimate, trying to select the right settings, you often end up having to do, like I said, 10 different ones, 10 different hyperparameter settings. But what if you have, like it's an infinite space of the parameter, something like the C value on a support vector machine, right? C is in the reals, okay? So there's an infinite number of them. You can't check all the possible C values. So what are you going to do? Well, if this is say this is C on this axis, and maybe this is the sigma on the radial basis function, then what we can do is we can tile it up and we can try on a regular grid all these different values. Okay? And the idea behind this is that we're going to do an exhaustive search. We're going to set up all of these values that are a grid of however many by however many. It's computationally expensive. You can end up with the fact that the best performance level is in between your grids, so you totally miss it, right? So on the plus side, you can run it in parallel. So each one of these different, models can be run on its own CPU simultaneously, right? So a slightly different attack that you can do is you can do a randomized search. So in contrast to the regular grid, if you just pick a value on each axis with uniform probability distribution, okay, so you pick, this one by chance, and you pick that one by chance, and you end up with that data point, and you just do that over and over and over again, you know that this is nice from the standpoint of you can just do this until you're like, I'm done. I don't want to spend any more time on this task, okay? So you're searching based on a time budget, and you're going to get the best answer you can in that time budget. So as always, when we're dealing with n dimensions, right, just like in the k-nearest neighbors case, the more the dimensions, the more hyperparameters you're trying to tweak at once, then the more samples you're going to need to get an accurate coverage of that high dimensional space. In fact, if there are n dimensions, you are going to need 2 to the n samples to cover it well. Okay? Or I should say proportional to that. So be wary of high dimensionality, but if you're going to do high dimensionality, a grid is probably a fairly poor way to do so. All right. So I think at this point what I want to do is stop the recording, and I'm going to come back to you in a separate recording and do a little bit with a notebook to show you examples of how to get this stuff done. Okay? Thank you very much. Bye for now.